Why did the star keep going to school? So it could get brighter. Stellar evolution is defined as the way that stars change with time. A star's evolution mainly depends on its mass. When dense molecular clouds begin to collapse, a star is born. The only thing that can cause a molecular cloud to collapse is an outside disturbance. These disturbances include nearby supernovae, death of a nearby sun-like star, density waves in galactic spiral arms, or galaxy collisions. The clouds fragment and each section collapses under its own gravitational force. This gravitational collapse can be distorted by the rotation of the cloud fragments or their magnetism. As the cloud contracts, the temperature increases, it speeds up its rotation and becomes a flattened disk. When differentiated by large changes in temperature, there are 7 distinct stages of star formation. Remember the interstellar cloud collapse and fragmentation we discussed earlier? That's stage 1. The next stage is when the individual fragments begin to collapse. When the cloud becomes dense enough, there is no further fragmentation. Then, when the interior reaches about 10,000 Kelvin, it becomes plasma. Stage 4 is when the cloud becomes a protostar and it is first visible on the HR diagram. After this stage, planetary formation begins, followed by the core reaching 10 million Kelvin. Nuclear fusion begins and it is now a star. Finally, the star reaches hydrostatic equilibrium and is stable in its position on the main sequence for 90% of its life. A star's position on the main sequence, life expectancy, and life cycle mainly depend on the mass. For small stars, stars with a mass smaller than 1.4 stellar masses, its life cycle can be trillions of years. When the hydrogen fuel in the core of a low-mass star runs out, it has reached the main sequence turn-off point. Hydrogen fusion occurs in a shell surrounding the core. The only thing left in the core of this dying star is a substance called helium ash plasma, helium nuclei produced by fusion reactions in a deuterium-tritium, a combination of hydrogen and helium. This helium ash builds up in the core. As this ash builds, so does pressure and temperature. After a helium flash, a brief nuclear fusion of helium into carbon, core helium fusion begins. The hydrogen shell and helium core continue fusion until the ash in the core becomes carbon, and helium shell burning begins to happen alongside the hydrogen shell burning. As the outer layers fluctuate, the carbon ash compresses. The outer layers shed in a planetary nebula. A white dwarf is all that remains. As a recap, the stages are subgiant branch, red giant branch, first dredge up, core helium flash, horizontal branch, pre-asymptotic giant branch, and finally the asymptotic giant branch, a second red giant phase. For a star of medium mass, between 1.4 and 3.2 stellar masses, the life and death is a little different. First of all, they live for billions of years as opposed to trillions. Initially, their evolution is the same as low-mass stars. They turn into red giants and undergo a phase of core helium burning. The core oscillates between compression and equilibrium. When the star's core fully becomes iron, nuclear reactions cease. Gravitational collapse takes over, strong enough to destroy the nuclei of the atoms making up the core. Enough energy is generated that the star goes supernova and can spread light years in every direction. What's left becomes a neutron star with a diameter of a few kilometers. The neutron star is so dense that a teaspoon of material on Earth would weigh a trillion tons. It can rotate up to 30 times a second and creates a giant magnetic field. A high-mass star, larger than 4 stellar masses, has similar early stages of main sequence turn-off as low-mass stars. These stars can live for millions of years. All of the stages of evolution from the subgiant branch to the asymptotic giant branch align with the stages of a low-mass star. The high-mass stars have a few extra steps. These are all stages of dredge-up, and the nuclear synthesis creates elements including iron, neon, magnesium, aluminum, lithium, and sodium. This high-mass star becomes a red supergiant, explodes in the form of a supernova rather than a planetary nebula, and turns into either a neutron star or a black hole, depending on mass. So, now that we've gone over the evolution of these different types of stars, Let's get into terms like the HR diagram and main sequence. What happens when the fragments are not large enough to become a star, and what star clusters are. Earlier in our overview, I mentioned something called the main sequence. The main sequence is a band on the HR diagram where stars spend the majority of their lives. It spans from the upper left to the bottom right of the HR diagram. The Hertzsprung-Russell diagram, often called the HR diagram, graphs the luminosity of a star versus its temperature. The HR diagram shows the evolution of stars of all different masses. The shapes of these paths are similar, but their place on the main sequence varies. Keep in mind that the main sequence is a band, not a line, because even if stars have the same mass, they can have slightly different compositions. These differences in composition can cause differences in both temperature and luminosity. Another important thing to note about the main sequence is that stars do not travel along it. They are fixed in their spot once they reach hydrostatic equilibrium, when the force pushing outwards equals the force of gravity, until their fuel starts to run out. Stars that form from the same cloud have the same age and similar composition. Thousands of stars found relatively close together with these similarities in groups are called star clusters. There are two types of star clusters. Open star clusters contain many new young blue giant stars. The other type of cluster is called a globular cluster, which consists of older, more spherical and stable red giant stars. There is an absence of massive main sequence stars in these globular clusters. These clusters can be blocked from forming by O and B stars blowing away gas and dust. This blowaway can also cause a cloud fragment to be too small. When too small, they become what's called a failed star. They are not massive enough to begin thermonuclear fusion. With a mass of between 12 and 80 Jupiter masses, these failed stars are called brown dwarfs. Larger than 80 Jupiter masses is when the thermonuclear fusion begins, and less massive than 12 Jupiter masses is considered a planet. Stars between these masses fuse hydrogen into helium in their cores in a process called core hydrogen burning. When there's no more hydrogen in the core, the star is no longer in hydrostatic equilibrium. It leaves the main sequence and begins to die. As the star dies, it expands, contracts, and finally explodes. Smaller mass stars die relatively gently, creating a planetary nebula and leaving behind a white dwarf. Larger mass stars die explosively, creating a supernova and leaving behind either a neutron star or a black hole if the mass is high enough. There are two classes of supernova, type 1 and type 2. Type 2 supernova come from the stars that were at least 8 solar masses at the time of their dying. These stars are found only in spiral galaxies, typically near the arms. These are the classic explosion one thinks of when they hear the term supernova. Once iron fusion occurs and more energy is needed than produced, the core begins to collapse in on itself. If the core's mass is less than about 3 solar masses, the collapse continues until the core reaches a point at which its nuclei and free electrons are crushed together into a hard, rapidly spinning core. This core consists mainly of neutrons and is thus deemed a neutron star. Detonation occurs when the material falls in from the outer layers of the star and then rebounds off the core. If the core is larger than 3 solar masses, the collapse is too large to become a neutron star and ends up becoming a black hole. The other type of supernova, type 1, is divided into 3 subcategories based on their spectra: 1A, 1B, and 1C. 1A supernova are thought to originate in binary systems consisting of a moderately massive star and a white dwarf, with matter being pulled from the massive star to the white dwarf. If the flow of material raises the mass of the white dwarf to above 1.44 solar masses, a thermonuclear explosion occurs. The white dwarf in this supernova explosion is believed to be destroyed completely. The cause of explosions for the other two types in the type 1 group are unknown.